Today I would like to go over intersection theory. And what is intersection theory? Well, intersection theory is the study of intersections of two or more objects and their expected results within a Euclidean region or non-Euclidean region. And for today's example, we'll be using a Euclidean circle. The first part of this I'd like to go over is the intersecting chord theorem. This theorem is given as AS times SB equals CS times SD, where for AS and SB and CS and SD, you have two inscribed angles or inscribed triangles in the circle. You actually can prove this idea yourself by using inscribed triangles. You can take the triangles for A, B, C, D and actually write them out in inscribed angles and verify this yourself. This is a great way to visualize the proof because at first it doesn't make much sense. Now that we have the fundamental idea out of the way, we can go ahead and look at a situation like this, where for each chord you have n plus 1. So for each region you add 1 and then add 2 and then add 3 and so on and so forth. But you might be asking to yourself, why does this matter? What does this have to do with mathematics? Well, we can use these inscribed triangles and intersections to look at a topological shape, given this one for instance, and actually measure for each intersection between not only the circle, the chords in themselves, but for each direct Euclidean shape within the circle. That said, these chords are arbitrary and they do not pass through the chosen best region for the circle given. Now, I want you to pause and try to find the best fit, because there's a certain line here that passes through the absolute best region for this circle, and it's great practice overall. Okay, assuming you found it, let's take a look. The overall goal with this is to find the optimal slices. So for the most slices to create the most possible topological regions within our shape. Now, imagine you're adding n number of chords. So you have any given number of chords intersecting through the best fit. And the best fit region obviously gives you the most possible regions per chord intersection. So how would we show this algebraically? Well, we could use this given equation and actually work it out, and that gives us, for each number of n chords, the exact value for new regions within this topological structure. And this idea of, infinite sums is a massive component of not only algebraic topology, but algebra and other fundamental mathematics as well. And I thought it's just quite interesting structure and components beyond just the idea of intersecting chord theorem. And for our final practice question, I would like to imagine a circle. Give yourself any circle of a given size. The numerical size doesn't really matter. And I want you to intersect any amount of chords and find the absolute amount of regions for each chord intersection you have. So let's say you have a circle and 5 chords. What I want you to do tonight is go through, draw out the topology of this and really visualize the chords, and let yourself compute this mathematically and geometrically. And I feel like this builds a massive amount of intuition for not only the concept of intersection, but the algebraic intuition that comes along with it.